My name is Aditya, and today I'll be talking about my research paper. Starting off with the introduction. So, to give some background, so modern vehicles nowadays they are increasingly dependent on wireless communication for things like navigation, also like safety systems, traffic coordination, autonomous driving, and communication with other roadside and other cars, like generally in like the surroundings around them. So the applications need to be strong. They need to be reliant and energy efficient because it's essential when a car is moving for the system to be acting very efficiently. However, the problem is that communication becomes harder when a vehicle is moving quickly because the wireless channel that is sending the signals changes rapidly. So the signals become blocked by other buildings or other vehicles, and the transmitter's information on the channel will also become outdated. So it's harder for the transmitter to pick up the right signals. So the current landscape of communication, especially in vehicular systems, is called massive MIMO, which is basically massive multiple input, multiple output. It's like the acronym. So it's basically where a base station uses many antennas to focus signals towards the user. So this is a process called beamforming. So how it works is that the waves match up, and so the waves match up in phase, which is like their angle and their like direction, and they add together and target the user, which creates a strong beam of energy pointing right at the person, and it's called constructive interference. So at the same time, the waves also cancel each other out in other directions, which is called destructive interference, and this lowers the interference for users in different locations. So it creates a more targeted signal towards the user. Another thing in massive MIMO is channel state information, or CSI. It's basically where the base station sends a known pilot signal or initial signal. The user device will measure the signal and then send back like a report. So the report basically tells the base station how the signal changes in space and time. So this is essential for the base station, so because it helps understand how like the information about the channel and how to send the signal. So this can improve Massive MIMO uses beamforming and CSI to improve the performance, but it may struggle when the direct path to the vehicle is weak or blocked, which is exactly what happens in vehicular movement. So to combat this, the new technology called RIS, a reconfigurable intelligent surface, has been created. It is basically a surface made of many small controllable elements, and what it does is it redirects wireless signals toward the vehicle, creating an additional reflected communication path. However, passive, so that there's a few types of RIS, which is active, passive, and hybrid. So I'll cover each of them. So a passive RIS only reflects and adjusts the phase of the signal, and the phase of a signal is basically like the position of the wave. So because it only does that, it uses very little power, but so that's a positive. However, it does not amplify the weak signals. An active RIS on the other hand uses active elements which amplify the signal. However, in the process, it consumes more energy and introduces something called active noise, which I'll cover later. So my research paper is more focused on hybrid RIS, which is basically a combination of active and passive. So it uses mostly passive elements which reflect the signals with low power, but also a few active elements which amplify the signal. So the main question is whether the hybrid design poses an advantage over a passive RIS, massive MIMO, or active RIS. So the metrics I'm using to determine which is the best is essentially those four that you see: spectral efficiency, which is basically how much data can be transmitted using the available bandwidth; then outage probability, which is how often the connection fails to meet a required performance level; also energy efficiency, which is how much data is delivered for the power consumed; and signal to noise ratio, which is like how strong the useful signal is compared with noise. So yeah, that's the background. I'll move on to the introduction. So the aim of this project is basically so the statement is written on the slide, but the main aim is to evaluate whether a hybrid active, which is both active and passive, a hybrid RIS can improve vehicular massive MIMO communication compared with a passive RIS and conventional massive MIMO without an RIS. And I want to do this especially under realistic conditions, which include imperfect CSI, vehicle mobility, and active element noise. So to clarify what those means, CSI I have already explained. So imperfect CSI is when the base station does not know the channel well. Vehicle mobility is when it's moving, and active element noise is essentially where the noise that's generated from using a lot of active elements. So the goal is to determine which architecture provides the best spectral efficiency and outage performance, which I've mentioned before, and how the vehicle speed, CSI error, active element ratio, and the active noise affect the performance. So here, active element ratio is basically just the ratio of active to passive elements. Then we also have whether RIS offers a worthwhile advantage over passive RIS, which is the main goal, and what portion of active RIS elements. So the right ratio. So I'm trying to determine the correct ratio for the best balance between communication performance and energy efficiency. So moving on, we have the method of my project. So my project basically uses a computer-based Monte Carlo simulation to compare the three vehicular systems. So a Monte Carlo simulation is basically a method that covers a wide range of possible outcomes, and it uses a lot of random sampling and uncertain variables. So my main idea with using this was to more closely replicate the randomness in a real life scenario. And so I compared three systems here: conventional massive MIMO without an RIS, massive MIMO with a fully passive RIS, and massive MIMO with a hybrid RIS. So for each trial, I used a random wireless channel and generated it for the direct base station to vehicle link. And where applicable, I also did the reflected link through the RIS. I also covered path loss, which is basically since the signal is being transferred from across three stages, there's two different paths it takes. So it goes from base station to RIS and RIS to the vehicle. So in both cases, there's a path that it has to travel, and naturally there is some path loss, or it's called attenuation. So I've accounted for that also, which weakens the signal. There's also blockage, which happens due to environmental structures, vehicle mobility, Doppler effects, which is a change in frequency as the car moves, and also channel estimation errors, which I've covered before. And I applied all this to make the model more realistic. The base station uses the estimated channel information to form its beam toward the vehicle, and the RIS adjusts the phase of its elements to strengthen the received signal. And in the hybrid RIS case, some elements also amplify the signal, but I accounted for the extra power consumption and additional noise. So the simulation varies a lot of key parameters. I've mentioned the parameters there. One is vehicle speed, CSI estimation error, the proportion of active elements, active element noise, the number of base station antennas, and the number of RIS. So I also ensure that each configuration is tested over many independent channels, and the average results are then calculated to reduce the effect of random variations and outliers. So the results are plotted, and then I plotted them using a graph. And then I analyze them to identify the performance trend. So this basically allows my project to determine when hybrid RIS performs better than passive RIS and normal MIMO, and whether the added performance justifies the increased energy use and noise. As you can see here, this is just some screenshots from the code. I used Python mainly for the simulation, and I did it on Google Colab Notebook. I generated over 1,000 trials, and it was a lot of trials, so it's very accurate data as well. Yeah, so that's just evidence of the code. So moving on, I'll be talking about the results. So here I've generated a lot of graphs. So I've just put all the graphs. I'll explain all of them individually. So firstly, we have spectral efficiency versus transmit power. So we can see that this graph basically shows how much data each system can transmit per unit bandwidth as the transmit power increases. So all three systems improve as the transmit power increases from 0 to 30 dBm, because a stronger transmit signal provides a higher received signal to noise ratio, and the relationship is increasing and slightly non-linear because of the logarithmic relationship. So the performance order, as we can see here, is hybrid RIS is number one, then passive, and then baseline massive MIMO. So the passive RIS performs it improves performance by creating an additional reflected path, while the hybrid RIS performs slightly better than that because its active elements amplify part of the reflected signal. However, the difference between passive and hybrid is very small, as you can see. It's almost barely noticeable, which means that under these settings, active amplification provides very modest spectral efficiency gain. So the main conclusion is that increased transmit power improves all architectures, but RIS resistance systems perform better than the baseline massive MIMO. So moving on, we have outage probability versus transmit power. Here we can see that the outage probability, it basically measures how often the performance falls below the required threshold. So lower values are considered better. We can see at 0 dBm, all of them have an outage probability of around 1, meaning that almost every transmission fails to meet the target. And it shows that the RIS assisted system becomes much more reliable at a lower transfer power than the baseline system. And the hybrid RIS gives the lowest outage probability because its active elements are strengthening the reflected signal. And by 10 dBm, all the outage probability is approximately 0 for basically all the systems. So the main conclusion is that RIS is valuable at low transmit powers, where it sharply reduces the probability of communication failure. However, limitation we can see that the selected outage threshold is pretty easy to satisfy above 10 dBm. So the curve becomes completely flat, and we cannot really distinguish the systems at moderate or high power. So that's one limitation with this graph. Moving on, we have energy efficiency versus transmit power. So the energy efficiency measures basically how much bits are transmitted per joule of energy. So that's the metric. And we can see that the passive RIS has the highest energy efficiency, which is a very key finding. And this is because it basically improves the received signal and consumes less power, as I've established. The hybrid RS surprisingly has the lowest energy efficiency, even though it has the highest spectral efficiency. So this is mainly because its active elements require so much circuit power and amplifier power. So the additional data rate gain is not large enough to make up or compensate for the added power consumption. But the energy efficiency rises with transmit power to approximately 25 dBm, and then it levels off or decreases. So the main conclusion is that hybrid RIS maximizes the communication performance, but passive RIS provides the best energy performance balance. And this is a very important graph that helped arrive at the conclusion. So the main trade-off here that we can understand is that the architecture with the highest spectral efficiency is not necessarily the most energy efficient, which is also a factor that you have to consider when we're determining the best option. So moving on to spectral efficiency versus vehicle speed. So this graph basically determines the effect of moving in a car, so vehicle mobility. And we can see that the spectral efficiency decreases as the speed rises for all of the three systems. So the faster movement basically provides increased Doppler effects, which is the changing frequency as the speed increases, and faster channel variation. So at high speeds, the CSI becomes less and less perfect. And so the massive MIMO it becomes harder for it to beamform, and the RIS phase adjustment is also harder because of the faster movement. The hybrid RIS is still the best performing system at every speed, and it's a pretty clear difference, followed by the passive RIS and then the massive MIMO. However, all three of the systems they do lose performance as the mobility increases, and the RIS systems appear to experience a slightly larger decrease. This makes sense because the RIS assisted links depends on both the base station beamforming and the RIS phase. So there's two phases. So the channel imperfections and the channel changes affect more parts of the transmission process. So that's why there's a greater decrease. So the main conclusion here is that vehicular mobility reduces performance, but hybrid RIS maintains the best spectral efficiency, which is good. Moving on, we have spectral efficiency versus CSI error. So it basically shows what happens when channel state information becomes less accurate. So as the CSI decreases from 0 to 0.2, we can see that the spectral efficiency decreases for all three. And this is because poor CSI causes the base station to direct its beam less accurate. So it causes the RIS phase shifts to become less accurate to the true channel. So the hybrid RIS here still continues to outperform the other two. However, its performance is still relatively small. The hybrid system shows like a bigger absolute, like a bigger loss, because the active amplification strengthens both the useful and incorrectly aligned components. So its performance depends heavily on CSI and accurate channel information. So that's why. But the CSI error reduces the effectiveness of beamforming and RIS phase control for all of them. But the main conclusion here is that the RIS systems outperform the massive MIMO, with hybrid RIS being perhaps the best option. Sixth, we have outage probability versus CSI error. So this is pretty straightforward. It's just all three are the same. It's just a straight line. This basically means that none of the channels fell below the selected outage threshold, even when CSI error was reached like a max of 0.2. But one key thing to note is that this graph does not show that CSI error has no effect. As we can see in the previous graph, it clearly affects spectral efficiency. Instead, it basically signals that the system performance remained above a particular threshold, even though it might have been changing, it just remained above a certain threshold. So this graph is probably not very useful, so I haven't really included it in my research paper. So moving on to the next graph, it's on the next slide. We have a few more. So the eighth one is hybrid RIS energy efficiency versus active. No, it's hybrid RIS spectral efficiency versus active ratio. So the active ratio basically represents the proportion or fraction of RIS elements that actively amplify the signal. We can see that adding more active elements increases the reflected signal. So the received signal noise ratio and spectral efficiency improve. However, the improvement is very, very, it's not large, it's pretty small. And we can see this by, if I just put into numbers, increasing the active ratio from around 10 to 75%, as you can see in the graph, it only produces a gain of around 0.2 to 0.26 in spectral efficiency. So this is pretty important because it shows the diminishing value of the system. A much larger number of active elements is probably required for even just a small improvement in data rate. So our main conclusion here is that more active elements do improve spectral efficiency, but the gain is very, very limited, especially compared to the additional hardware cost and power sacrifices. So eighth, we have hybrid RS, energy efficiency versus active ratio. This basically shows the opposite trend to the previous graph, and we can see that as the active ratio increases, the energy efficiency also falls quite sharply. This is because each additional active element consumes more circuit power and amplifier power because of the amplification that it does. Although the spectral efficiency improves, the improvement is very, very small to compensate for the total power consumption. So within the tested ratios, in my research, I figured out the best, most energy efficient option is therefore the lowest active ratio, which is around 10%. So this graph does not show the peak at a moderate active ratio. Instead, the energy efficiency decreases basically the same over the tested range. So the true value, like the true optimum value, could be below 10%, but I didn't test below the 0.1 active ratio, so there's no point. So the main conclusion from this is that a small active ratio provides the best energy efficiency, but excessive active elements reduces the energy advantage, which confirms like one of the main hypotheses I had. Next, we have hybrid RIS sensitivity to active noise. So you can see here that the graph isolates the effective noise introduced by the RIS amplifiers. As the active noise factor increases, the spectral efficiency also drops significantly. But the active elements do not really amplify only the useful signal. They also introduce and amplify noise, which at very high levels, so at high noise levels, the additional noise basically completely overwhelms the benefit of active amplification in the first place. So at the largest active noise factor, we can see the spectral efficiency of hybrid RIS falls below the passive RIS itself, which is shown also in several earlier graphs. So it's an improperly designed active RIS is essentially worse than a normal passive RIS. So our main conclusion is that the usefulness of a hybrid RIS depends strongly on low noise active elements, because a lot of noise is very damaging. So active amplification is only beneficial when the noise is controlled. So that's the main conclusion from this. Moving on, we have a hybrid RIS active ratio under mobility. So again, here it just confirms that the best active ratio is 10%, as the graph literally does not change. It doesn't perfectly mean that 10% is the exact best optimum like 100%, but it means that among the active ratios tested, 10% gave the highest energy efficiency. I tested a lot of ratios such as 0, 2%, 5%, 8%, 10%, 15%, 20%, and 10% came out to be the best. So I think most likely it will be 10%, but there's a small chance it could be something else as well. So that's the main conclusion. We can move on to the overall interpretation, which is basically my conclusion. So I have three main points. To summarize all of the graphs, mainly it's that the hybrid RIS achieves the highest spectral efficiency. So to put into simple words, it provides the biggest gain and usually the lowest outage probability. So it's also one of the most effective because the active elements strengthen the signal. But the passive RIS achieves the highest energy efficiency because it provides a large gain compared to baseline massive MIMO without the power consumption and amplifier noise associated with active elements. So the hybrid RIS is most useful when, so the main conclusion is that the hybrid RIS is the primary goal, and it's most useful when the maximum data rate or reliability is your main goal. But a passive RIS or a hybrid RIS with a small active fraction is probably a better option when energy efficiency is your primary goal and you want to save money for your energy. So the results basically prove that more active elements are not automatically better, which is the main finding from this. And it shows that increasing the active ratio slightly improves the spectral efficiency but sharply reduces energy. So because high active element noise can completely get rid of the advantage that hybrid RIS provides. So yeah, that's it. Thank you.